Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 1, we want to talk about fluid motion, the final part in which we will discuss about motion of matter, and we will later start to transition towards the transfer or the motion of energy and heat and temperature, which is the whole world of thermodynamics. So before we get started, please consider subscribing and also liking the video as it means a lot to me and as well to encourage me to create more videos about physics. And also the lecture notes will be in the description. So without further ado, let's jump into the discussion. So first we want to talk about density, rho, and pressure. So what is density? So we have already discussed some ideas using density while we haven't truly defined what density truly is. So density in here for fluids is basically the mass over a unit area, a unit volume, V. So this basically states that what's the mass of an object within a unit volume. So this idea can be used to actually to sum up a whole system just by taking small parts and measuring their mass and combining them all together to get the idea of what the fluid will behave. So that's the idea of density. And another one is pressure. And pressure is basically the normal force per unit area over a unit area. And this can be written as F over A. So basically, within a fluid, it is much more conventional for you to take the idea of density for your mass and pressure for your forces. And so here is a good question to ask. Is pressure a scalar or a vector quantity? The answer is it is a scalar quantity because if you actually define something to be at a certain point, it might have a certain pressure. Here, let's state 110 kilopascals, while in the other it's 1 kilopascals. And it is always the normal force, so it doesn't really have a true direction anyways. So, in here I have already given a example in which I have a point here in between the boundary of the 10 kilopascal and the 1 kilopascal. The question is, where would the particle move towards? The answer is the particle will go towards a lower pressure. So the idea that a particle would go towards a lower pressure is the idea of fluid mechanics. So the best way for you to understand this is that this 10 kilopascal will be later multiplied by the area of the object, which we'll call A, and then if you actually see that the normal vectors here, this guy will have 10 times the force compared to this guy. So that means it will experience about 9 times the force that is experienced by the object. Basically, that's the main idea. So, what's the unit of pressure? So, basically, if you actually think about for the density, it is normally idealized to be kilogram over meter cubed, but for pressure, it is normally newtons over meter squared, or this is defined to be a Pascal. But people normally uses another type of unit, which you call as the atmosphere. So 1 atmosphere is equivalent of 101.3 kilopascals. So this is the conversion factor that you need to use to convert atmosphere into pascals. And why do you use pascals? No, sorry, why do you use atmospheres instead of pascals, which is a standard unit? Well, the idea of a atmosphere is that it is the pressure that you experience in the Earth's surface. So, using this idea, you could get the feeling into if if you are having about twice the atmosphere that you feel currently. So that's the idea of actually using atmospheres instead of pascals. So so after we have already talked about this entire idea of density and pressure, I want to talk a little bit about properties of fluids. So fluids are basically anything that flows. And there are two types, incompressible as well as compressible. So what's the difference between those two? So incompressible fluids are fluids in which if you try to push harder, no, sorry, if you try to contain them within a volume and then you try to shrink the volume, it couldn't be done because the fluid doesn't truly compresses. And this is the definition of liquids. So the idea is if you have a bottle of water full and then you try to squish it, the the volume of the water doesn't truly change. In fact, it only changes shape while still maintaining the volume. But this is not true for compressible fluids or gases. Oh, uh, gases. So gases can be compressed. So one of the examples is that if you have a empty water bottle and then you crunch it up, you could have it to be contained within a very small volume while you are holding a high pressure gas. So when you release the cap, it will later make a booming sound, which is basically the idea of this pressure gradient in which the gases from the inside want to travel outside because of the pressure difference. So those are the difference between a incompressible fluid as well as a compressible fluid. So we want to start to talk about hydrostatic equilibrium. So hydrostatic equilibrium is in which your fluid will remain at rest. This doesn't mean that the particle would remain at rest, but the entire fluid doesn't change its properties over time. So one of the properties that you need to understand about this is that basically the change in pressure should be zero. And no, sorry, my bad. The sum of the forces should be zero because we are within a equilibrium. So, so I want to start to discuss the hydrostatic equilibrium that is achieved by gravity that you always see in everyday life. So, if you have, for example, a bottle or something, maybe a barrel or a beaker filled with water, and the question is, what's the pressure within a certain distance from this surface H? So that's the thing that I really want to try to derive for you in this video. So let's start to think about what are the forces that is present within this entire fluid. So let's actually try to design a slice of this water, which I will be modeling it to be some form of a disk with area A and a height called delta H. So there will be weight that is that is experienced by this fluid, but also there will be normal normal forces from the underside. So normal force from the downwards. Okay, let's just actually make that to be negative, and the normal from the positive. No, actually, let me just write it like this. The normal going in the positive direction and the normal going in the negative direction. Well, there are some other forces such as the walls here that is containing the fluid, but you could say that it is symmetric, so it doesn't truly it doesn't truly changes the equilibrium within the y direction. It only changes a little bit of the equilibrium within the xz direction, which I will not fully discuss. So, first by first by looking at this, you would notice that this guy would have a mass, and that's all that you need to derive the entire equation that I give in the notes. So, first, to get the sum of the forces to be zero, that means that the normal that is going up subtracted by the weight of the object subtracted by the normal that's going down must to equal to zero. So that's the idea for a hydrostatic equilibrium in this place. Oh yeah, there will be gravitational force going downwards. Uh, from here, I will state that the change in the normal, which will be stated to be the normal force from the negative side subtracted by the positive side. And why is that? Well, it is because of the way that I will define the h. So the h is going down. That means that I will compare the one from the bottom and the one from the top. So from the bottom side, it will be the normal plus, that's delta. So delta n will be defined to be the n plus subtracted by the n minus. So you would get the delta n to be equal to the weight. So what's the weight? It's m times g. And what's m exactly? Well, m is basically the rho, the density, multiply that by the a, multiply that by the change in the height. So you could write this to be the change in the normal to be equal to rho a g delta h. So looking at this, you would notice that this change in n over a would later become pressure, right? Well, in fact, it is the positive pressure subtracted by the pressure from the one that's going down. So it's basically the bottom one subtracted by the top. And this will be defined to be delta P. So this comes from n plus over A minus n minus over A, which is basically the change of n over A. There we go. So basically, if you divide everything by A, you would get delta n over A, which is delta P, plus rho g delta H. And so you would get delta P over delta H to be rho g. And taking delta H to go near zero, you would get dP over dH to be equal to rho g. So that's the hydrostatic equilibrium from gravity. So you could see here that the pressure doesn't truly depend on the area. In fact, it only depends on the height. So if you do this for a liquid, which means that for liquids, if you get the rho to be constant, you can do the integration to be dP equals to rho g dH. And doing the integral, this starts from the initial point, which will be P0, and towards the pressure that I really want to find, called P, dP. This will equal to rho g, the integral, from 0 towards the point in which I'm interested, which I'll call h, dh. Doing the integral, we would get P minus P0 is equal to rho gh. So the pressure would be rho GH plus P0. So what is P0? P0 is the initial pressure that you obtain from this top side here. So that's the idea of pressure, is that you could actually just sum it all up within the slices and you would get rho GH plus the initial pressure, which you call as the atmospheric pressure. This is atmospheric. And it is normally said to be about 1 atmosphere. So that's for the hydrostatic equilibrium from gravity. And so there are multiple different ways for you to use this idea. And one of them is the idea that you could create a pressure meter by using hydrostatic equilibrium. So one of the idea is to use mercury. So if you have this is a test tube filled with mercury, and it is contained within some form of like a beaker filled with mercury as well. There will be pressure from the outside that will be P0, and the pressure from P0 should be equal to the pressure that is exerted by this entire column of mercury, plus the atmospheric pressure in here, which is normally vacuum. And why is that? Because you can just fill the entire test tube with mercury first and then flip it over and make sure that there's no gas leaking inside towards the pillar of mercury. So you would get an accurate reading in terms of the height of the mercury. So this will later be, so if you actually try to solve this, this is basically P0 equals to rho GH. So, for example, if you have P0 to be from the outside, that means that the rho GH should fill the same amount. So the H should be P0 over rho G. And I believe this value is about 760 for 1 atmosphere. You would need to check it again. But this is the idea of using millimeter mercury, as this is one of the units of pressure. And this could also be referenced into torr, I believe, or bars, I believe. And so this is the idea where you could use hydrostatic equilibrium to measure pressure. So this is one of the ideas. And another idea is to actually, if you have, for example, a U-tube here, and then there will be, so this will experience atmospheric pressure, and this is the pressure that I'm trying to find. So it will later push a little bit of fluid, while in here it will be pushed by this atmospheric pressure. And you could figure out what's the pressure in here based on the difference in the height. So if you actually think of this to be P0 plus rho GH, this must be equal to the P. That's basically the idea. Well, sorry, this should be delta H. So you could figure out what's the change in the pressure thanks to the hydrostatic equilibrium. So that's another idea that you could use hydrostatic pressure. So the instrument above is called a barometer, while the bottom one is called a manometer. And there's also another type of instrument which you call as a gauge pressure, which basically measures the excess pressure above atmosphere. So that's the idea of you measuring pressure. So now I want to talk a little bit about certain laws. One of them is Pascal's law, and the other is 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 the buoyancy force, which I will later discuss by the Archimedes principle. Archimedes principle. So Pascal's law states that pressure increase is felt all across the fluid. So how do you actually prove this? So one of the idea is to take the dp over dh that you got, which is rho g. You know, you, you know about this. And so if you actually add a little bit more pressure towards the system, you would notice that the change in pressure over the change in height won't really change. In fact, if you later try to solve the equation, it it will later only add a little bit of a constant, which is the change in pressure. And this change in pressure is felt throughout all different points in H. So one example is that if you actually solve this, this is P equals to rho GH plus P0, right? And so if you add this at the input of your fluid to add another delta P, here you could see that the entire function is still linear. This is the original plus another change in P. So that's basically the idea of Pascal's law. So after we have already talked about the Pascal's law, I want to talk about the buoyancy force a little bit, and I will later define what the buoyancy force is through the Archimedes principle. So basically the buoyancy force is basically a force that keeps that uh, that is exerted by the fluid. Basically, that's the idea. So basically, the interaction between fluids is called the buoyancy force. And one of the ideas in the buoyancy force is the Archimedes principle. Archimedes principles. So the way that I will introduce this is assume that if you have an iceberg like that, you could see there are fluids there, right? And then if you actually think about this, there will be weight going down. And because this is in equilibrium, assume that there is a force, buoyancy force going upwards. Okay, this makes sense. It shouldn't move after all. Okay. And so now if you change this by taking this ice out and instead filling it with water instead. So this is all water. This is ice. It will experience the same weight. No, sorry. You could see that the interaction between the fluid and the object is still the same. So therefore, your buoyancy force is the same. But here's the idea. The weight should also be the same because of this idea. So with this crazy simple not assumption, but definition that the buoyancy force is the same because you have the same shape. And so the entire sums should be the same in the buoyancy force. Therefore, your weight should also be the same. So the idea that the weight of the water, no sorry, the weight of the displaced water should be the same as the weight of the object. That's the key idea for an object to float or sink. So if you have the weight of the displaced water to be much more smaller compared to the weight of the object itself, the object would start to sink until until it reaches a equilibrium, or unless you don't have enough volume from the object, which basically means that it will later sink. So that's the conceptual understanding of something floating or something sinking. So now I want to discuss a little bit about the buoyancy itself. So you might know an object to be sinking or an object to be floating. But what happens if the object is in between those two? That's the idea of neutral buoyancy. So if you have the object, so if you have the rho of the object to be the same as the rho of the fluid, it will be in a state that it basically is like in a free fall. So it doesn't sink nor float. So the way that you could actually see this is that if you got something like this, for example, this is fluids, and then let's just state that you have certain object here. Basically, this object is like it is not experiencing any much force. It is just floating out there. Well, you could say it is like within a place of non-gravity. I think that's the best way for me to describe this. So that's the neutral buoyancy. And and lastly, I want to discuss is the center of buoyancy. So what is this center of buoyancy? So like last time we have discussed about the center of gravity. And near Earth, it is basically the center of mass. The center of buoyancy has the same definition as the center of gravity, but instead it talks about what is the point that you could basically state that the buoyancy is felt. That means it also corresponds to the torque as well as the forces itself. So why do you need to understand the center of buoyancy? So here's the idea. If you have a boat, let's just take this as the bottom of a boat. You would have a center of mass and a center of buoyancy. The center of mass is going down while the center of buoyancy is going up. You could see that the forces wouldn't really cause the object to tip over because if the center of buoyancy goes a little bit to the right, that means that it goes a little bit deeper. The forces will help it to restore balance to make it upright again. But if you have, for example, your center of mass to be here and your center of buoyancy to be here, you could see what will happen. It will basically try to find a state in which it has a zero potential energy. No, sorry, the lower potential energy. So it will basically flip over, and you will have a ship that is going down, which is bad. So that's why marine engineers or like basically the people who create ships really need to think of the idea of the center of buoyancy, because if you don't understand about this, you might end up with a ship which just by sudden flips over. So that's the main importance in the center of buoyancy. Now let's start to talk a little bit about the dynamics. So we last time talked about equilibrium, but now we want to talk about fluids that are moving. So you might know about the Navier-Stokes theorem and whatsoever. So this is the basis for you to start to understand those kinds of systems. So first, I want to start with a little bit of definition. So streamlines are basically a flow velocity that is drawn in a continuous line. Continuous line. and the spacing measures flow speed. So why is this? I will later talk about this when we talk about the continuity equation, and this is related to it. So the way that you draw streamlines is that, for example, if you have, for example, the wing of a plane, for example, you could have like certain lines here, like so, that basically tells you where would the fluid would be going through. So you could see the fluids will be shooting off to a certain direction. That's the idea of streamlines. You basically try to understand if you have a particle within the fluid, how would it travel? And it is basically represented as streamlines. So for a steady flow, the flow is constant, is constant at each point. And if it is unsteady, well, that means it is changing, changes across time. So with this, we will start to try to understand about how fluids move in a steady flow instead of a unsteady flow, which might correspond to a turbulent flow. So we will start to discuss the continuity equation. And we first define a flow tube. So a flow tube is a tube region that is bounded by streamlines. And the ends in right angle to the flow. So one of the easy ways for me to actually to do this is that let's just have a pipe. You would know how a pipe would like actually have a streamline. It will go something like that, right? So I will just define this the furthest one to be our flow tube from here to here, and the one from here to here. So just by looking at this, we need to remember about certain properties in physics. One of them is mass. The mass is conserved. So that means any mass that you put in must be the mass that you put out, especially in a steady flow, because the system itself doesn't truly change over the time. So that means your mass should also not change over time. So the mass in and the mass out should be same. So m in should equal to m out. Okay, with this, let's start to think. So what's the mass in? So I will define the mass in to have this to have the end of this tube to have a1, while the blanket of this tube will have a distance called delta x1. Same thing here. Delta x2 and a2. And they will have density rho. Okay. So just by doing this, we could write, okay, so this is rho 1, this is rho 2. So the mass n would be delta x1, a1, rho 1 should be equal to delta x2, a2, rho 2. Well, because this might be a little bit long for me to write, let me just write delta x. A rho should be constant. It doesn't matter where you actually do this. You just need to make sure that this is constant anyways. So just by looking at this, the delta x might be uh it it might be something that you need to control, while the a and the rho could be defined straight away. But what about the delta x? Well, the easiest way for you to define the delta x is by actually taking velocity. So let's just actually divide the entire thing by delta t. Okay, so you would get delta x over delta t, a rho. And this would equal to the constant divided by by a certain value called delta t, which is still a constant. I'll call that c. So this delta x over delta t is something that you would notice. This is v times a times the rho. So with this, I can just rewrite this to be rho va is a constant. So if you have a system, you know its density, you know its velocity, you know its area, and then you have the other point, let's state, with certain rho and certain a, you could get the velocity, and vice versa for every single combination. So for any type of fluid, the rho times v times a should be constant. So that's the continuity equation. And this is the idea of a mass flow rate. This is what you call as the mass flow rate. And if you actually try to check the units itself, it makes sense. It is kilograms per second. It's like the amount of water that you put out, or like the amount of gas that you put out, for example. That's the definition of this continuity equation. It tells us that the mass flow rate should be constant anyways. So, with this, we could actually define a much more specific use in fluids. You know that fluids are incompressible. That means rho would be constant anyways. So with this, checking it towards your function, you would notice that the rho is constant. That means that you could divide both sides by rho and it doesn't truly matter. So you would get V times A is a constant. This is only for for liquids. So this is the definition of a volume flow rate. So if you check the units as well, you would see that the units is like meter cube over second. That's like the volume over time. So that's something which you call as the volume flow rate. And basically, if you know the volume flow rate of a fluid, no, sorry, of a liquid, you could also know the mass flow rate by only multiplying it by the density of the fluid, of the liquid. So that's a interesting thing for you to use in a fluid system. So now let's talk about the Bernoulli equation. So let's see here. Uh, the Bernoulli equation. Bernoulli equation. This is basically the conservation of energy. So how would I prove this? I will go and prove this by using the definition of energy. So let's just have, for example, another flow tube, something like that. This guy A, this guy has A. There's a difference in height. Let's call that from here to here, let's state. That's H. And from here to here, that's H, H2, H1. And then there's a velocity, V. Same thing here. So you could use the definition from the previous one to actually define what your what your system would be like. And so let's actually do this straight away. So first things first, there will be kinetic energy from the fluid itself. That will be half mv squared. Okay, that's interesting. You could add it by mgh, the potential energy of the fluid on average. You could just state that to be on average, or you could state it to be at the lowest point whatsoever. But I would define this to be at the center. After that, you would add it by the work, which is the force from the outside. So I will just put a force from the outside, which is normal towards the system. Multiply that by ds, the change in the position. And I hope this to be constant anyways. So the one in here and the one in here should be the same. So let's just state that you are also being given a small force going in that direction. Okay, so we could actually write this in a much more interesting way. So you could write the m to be half rho v. This is the definition of density of the mass, which is rho times v squared plus rho v, the mass again, gh, plus f1 times ds. And this is constant. This is constant. So let's divide everything by v. And obviously I will take the v to be a constant because, well, you couldn't really state that, but I will just divide the entire thing by a certain value called v. And the v doesn't really change over time. So we can just assume that the v is constant. So we would obtain half rho v squared plus rho gh plus f1 times ds over v. And this is constant, right? So here's the thing. What's ds and what's v exactly? And trying to think this through, you could actually define the volume of the system. I didn't state what the volume is. What's its area, what's its length. I just leave it up to interpretation. And this is where the coolest idea comes in. If you just assume the v to be a times ds, the area times a certain length ds, which is basically corresponding to the work, which still makes sense in here because a is the area and ds would be a very small fraction that is in right angle with the a. That's the ds that you come from work. So you could cancel those ds's out. So you would get the half rho v squared plus rho gh plus the pressure is constant. So this is a very interesting idea that you could actually figure out the velocity of the object only by knowing its position as well as the density as well as the pressure from the system itself, and combining the and also combining the equation from the continuity equation, you could actually manage to figure out what's the velocity just by only knowing its pressure, for example, and also the height. So that's a very cool idea. And so I want to actually to discuss a little bit about using the Bernoulli equation, because I see lots of people actually think that you use the Bernoulli equation in such a way that you actually assume that the tube itself is the rho gh, but instead it's not. So let's actually think of this. So one of the problem was something like this, you could see that there's this big area and there's this small area, and I would just put some form of like a barometer right over there. So if you actually deal with something like this, here is something for you to realize. So let's state if you if if you are already given, for example, the velocities, the rho's, and etc. So yeah, let's just state that you are given all of those. So, but I will just assume in here. Oh, okay. I'll I will just assume that the pressure comes from the outside straight away. This will be P0. Okay. So doing the doing the Bernoulli equation, you would get half rho v squared plus, for example, the height from here to here. We will call that h, and this guy would be 0. Let's just define it like that. So you would get half rho v squared plus the rho gh plus the p0. Okay, that's fine. This must equal to the half rho v2 squared. I will define that to be p2. Okay, you don't need to know about the area. But yeah, you could use the area for your continuity equation and just plugging it into your Bernoulli equation. And then the rho gh. Okay, what's the rho gh in here? Is it the height of this? No. In fact, the rho gh in here is actually 0 because the height is actually 0. But why do you need to add another rho gh which corresponds to the height of this small tube? Because it is actually measuring the pressure inside of this small tube. So what's the pressure within the small tube? That's rho gh. H2. H2 in here, for example. So that's what people always actually mix up. And if you actually think about it much more deeply, you could actually figure it out that it turns out it's the same thing. But the best way for you to actually to understand the Bernoulli equation is to actually to look at this example and actually realize that the height of this fluid actually only measures what's the pressure inside of this small tube. So that's something interesting for you to actually to remember. So I want to go into the application of fluid dynamics. And one of the things is actually the Venturi pipe. So basically the Venturi pipe is basically something like this, in which there's a constriction, and sometimes you actually put some form of fluids in here, so you could measure what's the velocity, thanks to knowing the pressure gradient as well as the area. So with that, you could actually figure out what the velocity of the fluid is, and you could get your mass flow rate, for example. So that's one of the uses in a Venturi. And so another thing that you could actually think of the Venturi pipe is like, for example, if you actually spray your garden with a hose, you would normally choose a hole which is smaller compared to the actual hose. So if you actually just take off the end of the hose, you could see that the fluid itself is not traveling that far. It only has a certain velocity. But if you actually close it with a very small area, you could actually see that the water will flow much more rapidly. And that's one of the uses of Venturi. Another thing is that talking about the Bernoulli equation comes the Bernoulli effect. So one of the ideas of this is that if you have a ball spinning, you could cause a high pressure in one end and a lower pressure in the other end, thanks to the Bernoulli equation. So if you actually try to solve it, even though this is very hard for you to solve by hand, even for me, I still don't know how to actually compute this. But based on the Bernoulli effect itself, you could know that there will be a pressure gradient. And thanks to that pressure gradient, you could see the ball moving. So that's why, for example, if you actually play ping pong, you could sometimes set the ball to be flying quite high or spinning in the air, thanks to the Bernoulli effect. And another use of the Bernoulli effect is the one that you use on planes. So airplanes have a very specific design, something like this. Is that in here and in here, right? And to generate a force going upwards called lift, you would need to have higher pressure here and lower pressure at the top. So you could compute this, but designing it is quite hard. And that's why you have aerospace engineers trying to understand fluid dynamics only to understand how could you get something off the ground. And this is what nature does that that creates wings. Is that how do you generate lift through the flap of the wings or through gliding and with the shape of the wings. So that's the uses in the fluid dynamics. So I want to talk a little bit about certain things that I didn't talk about when talking about fluid dynamics, which is viscosity and turbulence. So what's viscosity and what's turbulence? So viscosity is basically the friction between fluids. So water with water will have a certain viscosity such that it doesn't truly behave like the Bernoulli equation states. There will be certain aspects for you to actually to remember, such as the viscosity which will actually turn into heat and actually not only heat, because basically viscosity tells you about the interaction between fluids. One of them is, for example, the electrostatic force, which basically tries to pull fluids together. So it couldn't be truly be frictionless, basically. So that's basically the understanding of viscosity. And and this is no, sorry. And basically this is the thing that actually keeps fluids steady. Compare that if you don't have any viscosity. If you have a very small tweak in your condition, it might turn into turbulence, which is basically chaos. So this is one form of un, a unsteady flow. So if you don't have any friction between the fluids, it it might cause certain amazing effects, which you call as turbulence. So that's why air is much more turbulent compared to water. You could still control water much more easily compared to air, and this is because of the viscosity and it relates to its turbulence. So that's all for today's video. I hope that you learned a lot about fluid motions. And remember, if you want more videos, please consider subscribing as well as liking. And also, the notes of this chapter is in the description. So thank you very much, and I will see you on the next episode.